Hello, this online video is designed to be viewed after you've taken exam 2. It presents some additional topics that come at the end of chapter 4. I prefer that this material comes after exam 2 so that the concepts that I introduce here don't confuse you just ahead of exam 2. The other thing that is shown on this page is the assignment set that it covers section 4.6 from today's lecture, along with the start of chapter 5 that we'll be covering during the week of October 30th. In this video, you'll see I introduce 4 example problems, and I don't solve them as part of the video, but the solution to each of those problems that I introduce is available in the notes that accompany this video. In section 4.5, we cover moments about an axis. This is actually a fairly common situation. For example, anytime we're trying to use a wrench to turn a screw or a bolt, or to loosen a tire. What we're trying to do actually is to create that turning motion about a particular axis that is the line of the screw, or the direction in which the bolt needs to be tightened or loosened. When we're applying the forces or the couple or the moment to a particular wrench. In this example, the force P, the person is trying to apply a particular moment using this flex handle socket wrench. When you calculate the moment about the point A, does all of that moment provide useful effort in turning the screw? No, it doesn't. In fact, only the portion that's aligned with the axis of the screw is effective. But how would we calculate an answer to that? We'd have to take the moment that we actually apply, so you already know how to calculate moments about a particular point, and then find out what portion of that moment is aligned in the direction of the screw. So that's just a little bit more that we need to add on to what you already know how to do. So imagine, for example, a force that's being applied at point B, and we're wondering how it might cause the bracket to turn about its axis shown at point A. How would we determine the maximum magnitude of F that could be sustained before causing the bracket to turn on its axis at A? To do that, we'd need to know the calculations that we're about to introduce. In a scalar analysis, what we need to do is recognize that we already know how to calculate the moment of a scalar force. So we just take the force that's applied times d0, where d0 is the perpendicular or shortest distance from the point to the force's line of action. This concept can be extended to now find the moment of a force about a particular axis. Find the moment of an axis about the moment of a force about an axis can help answer the questions that we've just considered. In a scalar analysis of calculating the moments about an axis, we would consider this application, trying to loosen the nut on a flat tire. We might apply a vertical load F to our wrench and want to know how much of it's effective. How much of it is effective? Not all of it. We know how to calculate the moments due to F about the point O, but what we'd like to know now is how much of the moment that we create is actually in the direction that helps. That is, how much is in the direction of the y-axis. So what's the moment about that line of action? And to calculate that, we need the angle between our vector and the direction of that's the force is effective in. So we'll get to that calculation now. And the easiest way to do that is with a vector analysis. Our goal is to find the moment of F, that is the tendency to rotate the body about the A axis. So we know the direction that we want to find the moment along that particular direction or axis, and we need to calculate that using what we already know about how to calculate moments. So we'll start with that. What we do know about how to calculate moments, we know how to calculate the moment of f about an arbitrary point O that lies along the axis of interest. We just would take r cross f using the same procedures we learned earlier in chapter 4. But now we want to find out how much of it is aligned along the particular axis of interest. Now we need the unit vector in the direction of interest, that is, in this case, in the unit vector in the direction of the little a axis. And now we would use the dot product with the moment that we calculated by the earlier procedure. And what this actually turns into is a series of vector operations, which involve both the dot product and the cross product, as I'll introduce in the next slide. We can set this up by, to calculate the effective moment along a particular axis, we would need the unit vector of that axis, dot it with the result that comes from r cross f. Now, you already know how to do both those operations, dot product and cross product, but now we can put them all together in what's called triple scalar product. And to do that, we set up the 3x3 that's shown in this equation, and we would just calculate that determinant, and that would actually give us the triple scalar product, or u dot r cross f. So in this equation, u represents the unit vector along the axis of interest. R is the position vector from any point on the a-axis, the axis of interest, to any point on the line of action of the force, and F is the force vector that's being applied. We'll start off looking at examples of this process of calculating moments about an action. We're going to consider force F that's being applied to the tool as shown, and if we want to find the magnitude of the moment about the x-axis, our plan is going to be to use the triple scalar product that we just introduced. First, we'll need F in its Cartesian form. That's something we know how to do. We'll need the unit vector for our direction of interest, and we were just asked to find the magnitude of the moment about the x-axis. So we'll need a unit vector for the x-axis, which is straightforward, is 1 times I. And then we'll need a position vector from O to A. So from our origin along the axis of interest to A, the point where the force is being applied. With that, we then just perform the triple scalar product. So in our solution, we do have our unit vector. It's 1 times I. Our position vector from O to I is, when we're looking at that, notice that it only involves the J and K terms as shown in this figure. That is 0.3 meters in J or y-axis, in the y-axis direction, and 0.25 meters in the k-axis or the z-axis. If we have the direction cosines associated with the vector f of cosine 120, cosine 60, and cosine 45 as our direction cosines, using that format to determine the f in Cartesian form, we're able to make the calculation of f being is equal to minus 100I plus 100J plus 141.4 K, and that's given in newtons since our original force was given to us in newtons. Now it's time to find the triple scalar product. So we'll set that up using the determinant, where the first row is our u vector, and remember it was the x-axis, so that's 1, being only have a component in the x direction, so it's 1, 0, 0 for the first row. In the second row, we insert the r that we just found, so that was 0, 0.3, and 0.25. And for the last row, it's f, or minus 100, plus 100, and then in the third position, 141.4. With that, we then just calculate the triple scalar product, which is the determinant of that 3 by 3. And if you know how to calculate determinants, that's a straightforward process. And we would then end up with an answer of 17.4 Newton meters counterclockwise. And here we're going back in to having only a result that's in 2 dimensions. That is, when you're considering rotations about the axis, it'll either be clockwise or counterclockwise in the direction that you pointed that unit vector of the axis. And that's how we end up with a result in this case of 17.4 Newton meters counterclockwise. In the next example, we have a force of 30 newtons that's acting on the brackets, and we're going to be able to use alpha, beta, and gamma to use the direction cosine format to get F again. But our approach is going to be as it was before: find the unit vector of the axis, the position vector from the origin or some point along our axis of interest to the point where the force is being applied, and then we calculate the moment along that direction of the axis using the triple scalar product. Here we have the axis of interest being aligned in the j direction. We can get our position vector from our axis to the point where the force is applied, and here it only has components in the x and z direction, so we only have I and k involved. And lastly, we need F, which we can get in this case from the direction cosines. So we have our 3 components, we have our 3 different vectors. So in example 2, we're ready to calculate the triple scalar product. We can get the triple scalar product by simply creating this 3 by 3 and then finding the determinant, where the 3 by 3 contains in the first row the unit vector of the axis of interest. In the second row, we have our position vector from O to A, and in the third row, we insert our force in Cartesian vector form. So now we just calculate the determinant using the conventional methods, which I hope you've learned. If you haven't, you'll know how to do this later. But the good news is that this is an example problem just to show you how it's done, but I will not be assigning any problems from this section, and I will not be putting any problems of this type on any future exam. But I did want you to see this, because how we calculate moments so far isn't the way we actually find them most useful. This is actually more useful, but the technique's a little different, and I don't want to create the potential for confusion. That's why I introduced this material after exam 2. But now that we're done with section 4.5, it's time to move on to 4.6, moments of a couple. And here, what we're doing is we're applying 2 forces of equal magnitude, but in opposite direction, that are separated by a particular distance. In this wheel, we might grip the wheel with a wider grip or a narrow grip, the wider grip on the left or the narrower grip on the right. Both of these will apply a pure turning motion to the wheel or the nut at the center, and the question is, which one's going to be more effective? Turns out, and maybe you've done something like this so that you know that the answer is the one that's more effective is the one on the left. The larger that separation distance, the greater is your potential for turning the wheel or turning the nut in this case. When you grip a steering wheel with both hands and turn, you create a couple moment on the wheel. Question is, would older vehicles that didn't have power steering need a larger or a smaller steering wheel? Turns out the answer is you'd want a larger wheel to make it so that the amount of force that you need to apply, because the larger that separation distance, the bigger the wheel that is, the larger the moment couple that you're going to be able to apply to it. A couple is defined as 2 parallel forces with the same magnitude but opposite direction that's separated by what we'll call a perpendicular distance d. So that's what a couple is. The moment of the couple is defined then as the magnitude of the individual forces. Remember, both have equal same magnitude but opposite direction, but the magnitude without direction times d, that separation distance, gives us a scalar version of what that what moment that couple produces. The vector version of that calculation is r cross f, where r in this case is any position vector from the line of action of one force to the line of action of the other force. The net external effect of a couple is that the net force from the two forces being considered together is zero because they go in opposite directions. So the net effect being equal but opposite for those two forces pointed in opposite directions mean that there's no net force effect. But we still have a pure moment that comes from the turning tendency associated with F times the separation distance between the two forces. Now, notice that that separation distance has to be calculated in the direction that's the minimum, or the perpendicular distance between those two lines of actions of the forces. Since the moment of a couple depends only on the distance between the forces, the moment of a couple is what's known as a free vector. It can be moved anywhere on the body and have the same external effect on the body. And moments due to couples can be added together using the same rules that we had for every other 3D vector addition case. Now it's time to introduce some example problems, and I encourage you to try and consider each of these. And I'll briefly introduce them here, but the solutions are available to you in the handout that accompanies this lecture. So our plan, in this case, we're given two couples acting on a beam with the geometry shown. We're asked to find the magnitude of the force F so that the resulting couple on the resultant couple moment is 1.5 kilonewton meters clockwise. Our plan then would be to calculate the two couples to find the resultant moment and equate the net moment to what we know the sum to be, 1.5 kilonewton meters clockwise, to find the value of F in this case. What I'd like to point out is that one couple involves 2 kilonewton forces, one to the left and one to the right. The other couple comes from the force F pointed up on the left and down on the right. So notice that if you sum the forces in the x direction and the y direction, they'll come out to be zero in both directions. But we still have the potential for we will still have a pure rotational tendencies of 1.5 kilonewton meters clockwise if we choose F correctly. So see if you can work on that problem on your own, and you'll find the solution available in the handout. Our next example involves a 450 Newton force that's being applied on the pipe assembly shown. And what we want to ask is find the couple moment in Cartesian vector notation. Here we'll use the moment being defined by r cross f to find the couple moment. And we'll set r as the position vector that extends from A to B, that is from one point on the line of axis of the force to the axis of the other force. So any position vector of that type will give us the correct answer. And then we calculate the cross product used to find our moment of interest. In the third example, we're back to a 2D case. Here we have two different moments and we want to find the resultant couple. So we calculate the moment due to each of the couples and then add them. We'll resolve the forces. It's easiest to resolve them into components in the x and y direction so they can be treated as couples, and then we'll add these two couples to find the resulting couple. And the last example is a three-dimensional case that involves uh, these two forces, one 80 newtons directed up and 80 newtons directed down. And we're asked to find the couple moment acting on the pipe assembly using the Cartesian vector notation. Our plan is to calculate the moment, we need r cross f, where r is the position vector from one line of the direction of the line of action of one force to the line of action of the other force. And then we'll calculate the cross product to find the moment. The solutions are available in the PDF that accompany this video, and I encourage you to work on each of the problems on your own for a while before you check your work against the solution.